Okay, hi everybody. So we're gonna compute the two-dimensional volume of a sphere of radius r. And so this is also called the surface area of a sphere. Okay, so let's see, part A. This a little, let's zoom in a little bit. Okay, so to get volume, or two-dimensional volume of a sphere, we can integrate the integral over S of f. Let's call the sphere S, where f, it sends x, y, z to the number 1. Completely ignores the input and always spits out 1. If we integrate the function 1, then remember the little volumes of the pieces times f at some piece, this will always be 1. We're just going to sum up the volume of the pieces, which means we'll get the volume of the entire object, the sphere. Okay, so first thing in words, I just say, to get the volume, you just integrate the function that is constant and sends the function 1. You could call this the function 1. Maybe you could call it like that. Yeah, but this is what it is. Okay, so then the only thing we need is the change of volume factor. Then we only need a parametrization map and its change of volume factor, right? And actually, we know how to parametrize the sphere, right? That was problem 1. And so we can just sort of quickly rediscover this. We have some three-dimensional space, and we have some point here, and there's this triangle, which is a right triangle, and then there's this triangle, which is a right triangle. And let's call this theta 1, and let's call this angle theta 2. So I'm going to redraw. Here's theta 2. And what do I have? So if this is radius r, right, we have a sphere of radius r. So then the hypotenuse is r, and this is r sine theta 2, and this is r cos theta 2. And okay, so notation, this is just going to be much easier for this problem, is that C1 is cosine of theta 1. C2 is the cosine of theta 2. S1 is the sine of theta 1. S2 is the sine of theta 2. This will be much easier for us. Okay, let's go back to our picture. We also have this second piece down here. And this is theta 1. And now, what is this hypotenuse? Well, this hypotenuse is the same as up here. So that's r sine theta 2. And then opposite gives me a sine theta 1 times the hypotenuse, r sine theta 2. The adjacent gives me a cos theta 1 times the hypotenuse, which is r sine theta 2. Okay, and so this is all I need. I look back at my picture and I see that this is the x, this is the y, and this is the z. Right there. Okay, so then the map is theta 1, theta 2 maps. Let's call it, I don't know, G. And it should go to, well, x is r c1 s2, comma, y is r s1 s2, and z is r c2. Excellent. So all we need is the change of volume factor from this parameterization. Well, that means we need W1, which comes from the derivative of the first input variable. Now, remember that C1 is cosine of theta 1. So like the derivative of cosine theta 1 with respect to theta 1 is minus sine of theta 1. So the derivative of C1 is minus S1. And so we're going to get something like minus R S1, S2. This is a constant, so they just hang out. The cosine becomes minus sine. I do the same thing, partial theta 1, and what I get, a sine becomes a cosine, and the others hang out. Partial theta 1 gives me 0. There's no theta 1 here, so this gives a 0. Excellent. W2 comes from the partial, the second variable. This is the second column of the Jacobian matrix. And what is it? Well, partial theta 2, a sine becomes a cosine. Partial theta 2, the sine becomes a cosine. Partial theta 2, the cosine becomes a minus sine. Okay, great. So now I just need the gram matrix, which means I need to do W1.W1, W1.W2, W2.W1, W2.W2. This is the gram matrix of W1, W2. And then I'll take its determinant, and then I'll take its square root. So let's do, let's just make this smaller. I don't need that. So W1 dot W1 equals, okay, take this dot itself. That means I square this, and I add it to the square of this, and I add it to the square of this. Okay, let's simplify. Let's pull out the r squared, and I can pull out a factor of s2 squared, leaving s1 squared plus c1 squared. But cosine squared plus sine squared is 1. And so this is r squared s2 squared. Okay. So that's the first entry in our gram matrix. Let's do W1 dot W2. Okay, so now I multiply these and add it to a multiplication of these and add it to the multiplication of these. I'm just doing a dot product. Okay, so minus r squared c1 s1 c2 s2 plus, now I take the second ones. And this is wonderful because I get exactly the same thing but with a plus sign. And those will cancel. Plus, now the last coordinate, 0 times something, will be 0. And so this entire thing is 0. But that means that W2 dot W1 is also 0. Excellent. Only one more coordinate for our gram matrix. And that coordinate is W2 dot W2. What's that going to be? Okay, so let's take the sum of squares. This times this. Plus this times itself, plus this times itself. Okay, and now again, I notice that this time I can pull out an r squared and a c2 squared from both of these, and it'll leave a cos squared plus sine squared, which will be 1. That is 1. Okay, and then from these two terms, I can pull out the r squared, and I get cos 2 squared plus sine 2 squared, which is 1. And so the end result is an r squared, a 0, a 0, and an r squared s2 squared. Great, so let's take the determinant and then the square root. Okay, so the determinant of this Well, both these are 0, so it's just going to be this times this. That means I've got r squared times s2 squared. So r to the 4th s2 squared. Then I will take the square root, and I get r squared s2 squared, which, now if I want to, I can remember that this is like that. Okay, and then in words, I'll say, what did I just do? This is the, change in volume factor from our parametrization map. Okay. So great. Now, all it asks me to do is to set up an iterated integral that equals this volume. I already know that the function values are just 1. So all I need to do is integrate. Now, volume of the sphere will be equal to the integral of the sphere of the function 1, which will be equal to an easier integral over a rectangle, and this is the whole point of using the parametrization map, is that it is going to be an easier integral over a rectangle in the theta 1, theta 2 plane. So now, what rectangle? Go back here. See that theta 1 can just go in a whole loop from 0 to 2 pi. So I'll write theta 1 in 0 all the way to 2 pi. Just moving around in a loop, theta 1. And then theta 2 only needs to go down by pi. Because if we go all the way around again, we're going to double up the sphere. So actually theta 2 just goes from 0 to pi. Think about this. You need to think about why this works. If you don't believe me, then try it in a computer and you'll see you will double up the sphere if you let this go to 2 pi. That's too much. And you can really just think longitude and latitude. Okay. So great. So then we just do, theta 2 from 0 to pi, and then theta 1 from 0 to 2 pi of what? Well, the function values are just always 1, regardless of what we put in. So that's really easy. Composing functions, you just still get 1 every time. But we do need this change of volume factor. So let's do r squared sine of theta 2. Oh, you know what? I made a mistake. Look at this. Sine of theta 2 squared, square root. Well, that was a mistake. So this doesn't. Yeah, the square root of something squared is now to the first power. Okay, so this is the answer. I guess I can put the answer in. Great. Answer. If you can actually compute this by hand. I didn't ask you to, but the answer will be 4 pi r squared. And that is the surface area. This is how you discover the surface area of a sphere, by integrating. Yeah. Okay, good. Let's do part B. Set up an iterated integral that integrates the spherical harmonic x squared minus z squared over the sphere. So spherical harmonics have to do with the electron orbitals. And it's going to be so easy. Part B is very, very easy. So part B, we'll just notice that now instead of the function that gives 1 every time, we're going to use something else. So let's look down here. Part B. To integrate, let's call it f from x, y, z to x squared minus z squared over the sphere. We need to compose functions. And so we start with our parametrization map. And then we realize that, we realize that this is x, y, z goes to x squared minus z squared. So we can form a new map that just goes all the way. And wherever we see an x, we will replace it with this. So r squared, c1 squared, s2 squared. Minus, now a z squared gets replaced by this. c2 squared. And now, you could factor out the r squared, but it's not going to give you something that remains that can cancel very easily. So we'll just keep it like this. That's fine. And this is the function, well, if this is f, then this is f after g, which in Julia you can denote like this, where the symbol is /circ. It means compose the functions. In a computer, composing functions is very important. And also in math, it's very important. Okay, so, but you see, it's not, like, composing functions is not hard. You just plug in, wherever you see an x, you plug in these things. Very easy. Okay, so then our iterated integral is exactly the same. Just do theta 2 from 0 to theta 2 equals pi, theta 1 from 0 to theta 1 equals 2 pi. And now we have our change in volume factor, sure, r squared sine theta 2 squared, or sine theta 2. This is the change in volume. And then we multiply by our function values. Before this was all, the function values were just 1 everywhere. That's why we got the volume of the sphere. But now our function values are something like this. Okay, and if you wanted, you could write this out as like r squared cosine of theta 1 squared sine of theta 2 squared minus r squared times cosine of theta 2 squared. And this is this integral now calculates the integral of a spherical harmonic over the sphere. And you could just plug this into a computer and it will do the fundamental theorem of calculus once and then twice, and you'll have an answer. Okay. That's it. So you see you have words, formulas, and pictures. This is almost like a picture right here to compose the functions. But really the main picture was to parametrize the sphere.